Okay, everybody. For those of you who had to run to make it back to this meeting room from the coffee area, we have some bottles of oxygen for those of you out of breath. For the others, I would like to start the next session, and we start with an invited paper by the University of Maryland, William Nelson, Chen-Sheng Wu, Sprengel, and Christopher Davis, and it's called Propagation of Combined Laser Beams Through Atmospheric Turbulence. Chris.
So what I'm going to talk about this morning has actually become a matter of some controversy. And it all comes down to the different ways in which you could potentially make directed energy laser weapons. And there are different schools of thought about the way you do this. And there's been a lot of discussion about whether coherently combining laser beams is the way to go, or whether you produce your directed energy by other means. And for example, one of the other approaches, which I'm not going to talk about today, is something called spectral combining, where you actually have lasers at slightly different wavelengths and you combine them to co-propagate off a special diffraction grating, I'll call it. Okay? So I want to acknowledge that the primary author of this work is my former student, Billy Nelson, who fairly recently got his PhD and immediately got a job, which is good. And I also want to acknowledge the great help my current student who just got his PhD, Chen-Sheng Wu, has contributed to this work. And perhaps some of you know of Phil Sprengel, who recently joined the University of Maryland from the Naval Research Lab, and he's been heavily involved with directed energy for quite a long time. And in fact, he's been stirring up this controversy because he's a great believer in incoherent combining rather than coherent combining. So I'm going to try and talk about this. And of course, I must acknowledge the great deal of help that I get from other colleagues, because a lot of our current research is funded by the Joint Technology Office, and we have a big partnership with the group at the University of Central Florida, particularly famous Larry Andrews and Ron Phillips, because they have superb test ranges that we use to do a lot of our experiments. So the fact is that the Department of Defense is very interested in directed energy. And the plan is, apparently, they're going to pump a lot more money into this research area in the next few years. And of course, there have been systems already developed that I think they need to be improved. And, you know, it's interesting. I'm not sure that this is actually a picture of what used to be called the airborne laser system. But the airborne laser system was a system that cost a fortune. The program was canceled several years ago, but it was a megawatt-class chemical laser mounted on a Boeing 747 that was certainly brute force power delivery, but the laser itself was such a monster and so expensive and complicated that that program got canceled. But right now, both the Army and, of course, the Navy are very interested in directed energy weapons. And in specific, I would say that the Navy is the most interested because they're very worried about the threat to their ships from missiles that come in skimming the surface of the sea, very low down. And so you're faced with trying to engage a target that's moving through what we call deep turbulence, where the turbulence, the C sub n squared, can be very large, and the ranges are typically engaged within a few kilometers, and you don't have a lot of time to do it. So there's certainly a lot of interest in the Navy at worrying about directed energy weapons that work in deep turbulence. From the standpoint of lasers that fly on planes that are operating at higher altitude, in a way, their problems are not so severe, because if you're talking about shooting from a plane at other targets that are at altitude, the turbulence levels are much lower, and some of the things you can do are more straightforward than what you have to deal with when you're talking about deep turbulence. So you're actually going to see this slide twice, but I thought it was good to introduce it early on. This is one view of coherent combining. the idea is to make a high-energy phased array where, for example, you have a bunch of high-power fiber lasers, and you have to set them up with different piston changes and even tilt changes so that the wavefront that's coming out has imposed phase changes on it that's like an adaptive system. So the system compensates for the effects of the atmosphere as it propagates, okay? And of course, from a practical standpoint, and this, again, is what the Naval Research Lab does, in a real environment, you do not want to have a multi-kilowatt fiber laser with its energy just coming out of a small laser facet. Because if any contamination gets on that facet, you've got facet damage. So one of the approaches is actually you fuse a larger piece of silica on the end of the fiber, and then, of course, there's natural expansion of the laser beam leaving the fiber. So the fluence on this face here is not as large, and it's going to be more resistant to damage. And then, of course, you can have a collimating lens. And, of course, if this all works, you get a beam going downrange whose beam divergence is controlled by the overall size of the array, not just by the size of this beam. It's a combination of apertures that gives you a small beam divergence. And the question is, how quickly do you have to compensate these piston effects to deal with ambient effects? And how big do these have to be? Okay? The point is that fiber lasers have a very broad line width. So they have a very, very short coherence length. And so you've got to make sure that the phases of these beams are kept controlled with the differences you want to compensate for the atmospheric effects. And you have a limiting spacing between these sub-apertures that I'm going to talk about later as being very important in determining whether coherent combining is actually going to work. And this is the alternative approach. This is incoherent combining, where you just have all your lasers, and in fact, they don't have to be fiber lasers. I'm just using those as an example because in the world of directed energy, to some extent, they're the flavor of the month. It doesn't mean they may be the ultimate choice. In fact, one of the highest power actually deployed systems right now is a system on a Navy ship called HELADS that's 150 kilowatts, but it's based on slab lasers. But right now, there's a tremendous effort going on using fiber lasers, because with fiber lasers, if you run them all in a master oscillator power amplifier situation, you can actually make sure that they do fluctuate in phase with each other. So you can do the coherent combining, but as I'll say later, a very important parameter is how far apart they are in the actual launch geometry. Now, if you're doing incoherent combining, this will give you, in principle, a wavefront, but then you've got to send it off a deformable mirror to do the compensation for what the atmosphere is going to do. And I've drawn this as just one great big deformable mirror. But in fact, each of these beams from the sub-apertures could have its own deformable mirror. And the idea is you then aim them all at the target, and then you have two things you have to consider. Do you try and produce a really nice beam at the transmitter, or ideally, you'd like to have the best possible beam when it arrives at the target? You'd like to focus all the energy on the target. So in incoherent combining, you'd really want to steer all these beams to arrive on the target in the same laser spot and make those laser spots as small as possible so you have the maximum lethality of the target. Okay, so that's very important. So you've got to use deformable mirrors if you're doing incoherent combining, if you're going through any decent level of turbulence. But the coherent combining, in principle, can be used to compensate for the turbulence effects, and it does its adaptive optics by being a phased array. Now, I'm going to skip through these because some of these are sort of boilerplate slides, but, optical turbulence is going to affect the way these systems work. And these are very small fluctuations in refractive index. And as I'm sure you all know, there's all kinds of good theories about how we describe the turbulence. We've got an outer scale, an inner scale. We've got Kolmogorov variation of the spatial spectrum. Although, of course, in a lot of our recent modeling, like many people, we don't just use the straight Kolmogorov model. We actually use something called the Hill spectrum, which includes the inner and outer scale, and also some fine adjustments that have been made based on experimental observations. And like many people, and Mikhail will tell us we're all doing this wrong because we're doing phase screen simulation of what's going on. So, we're just solving per axial ray equation, and we're going to do the standard phase screen method where you have a bunch of phase screens and you look at the accumulated phase distortion as you go. And of course, the standard approach that nearly everybody uses is this split-step phase screen method where you have a phase screen and you impose on the phase screen the appropriate distribution of refractive index that has the right correlation functions. And then you propagate to a next phase screen and you keep on going. And of course, in principle, the more phase screens you have, the better the result's going to be, but of course the computation time goes up. And, if you look at what happens to the beam, this is all well known, I'm sure. If you propagate the laser beam in atmosphere, you get a nice beam on the target. Send it through turbulence, it gets messed up. Not only does it break up, it wanders about, it spreads, and you get all the nasty things that happen that reduces the amount of fluence that you're going to get on the target. And of course, this is what you want to correct, okay? And of course, how hard you have to work is influenced by how strong the turbulence actually is, okay? And of course, the Ritov variance is a number you can come up with which won't actually tell you how bad the scintillation is, but it gives you a canonical number you can use. And generally speaking, when you're getting into deep turbulence, this Ritov variance can get very big. I mean, I've heard people talk about this being as big as 7 or 8. Although, generally speaking, people talk about maybe it gets as high as something like 2. And the other parameter that's extremely important is this lateral correlation distance, which, everybody calls the Freed parameter, which is a measure of the size of patches where you don't have more than a certain phase shift, okay? And this number gets smaller and smaller as the turbulence gets stronger, okay? So here's some of the things that people have looked at doing to direct laser beams through atmospheric turbulence. We actually, some years ago, looked at whether Bessel or Airy beams had any advantages over Gaussian beams for propagating through turbulence, and the answer is they don't. It turns out that a Gaussian beam, if you can manage to preserve it as it goes through the turbulence, is the best kind of beam to propagate. And of course, you want to correct the beam distortions with adaptive optics. Now, the big problem with this is if you want to produce a high-quality fluence on the target, you've got to have some kind of metric about what the beam on the target is actually like. And most experiments to date have, I shouldn't be rude and say they've cheated, but they've used a technique which lets them prove principles. They put a corner cube on the target. Real targets that we may have to face with direct energy weapons won't have a corner cube on them. They're going to be diffuse surfaces. They may have glints. They're going to probably be machined metal of some sort, so there are going to be some unusual scattering patterns coming off those targets, but not necessarily a very clean way to get a metric of how much power there is in the target. And of course, the big controversy is, can you coherently combine a beam to get more fluence on the target? And of course, tied in with this is, what metric do you use to figure out when the coherent combining is actually good or not? So, fiber lasers are really good for for coherent combining because they fluctuate a lot, but they fluctuate in phase. And so, this is just an example of 7 coherently combined apertures. So this is at the transmitter. In the far field, you get one primary intense lobe with sublobes around it. And this is well known. And this is, of course, what you'd see in a vacuum. Now, depending on the kind of laser you're using, if you're using a laser that can't be controlled in phase, for example, certain slab lasers, and there are hypothetical new lasers being considered that aren't very easy to keep fluctuating in phase, and then they are really problematic for coherent combining because you can't control the relative phases of the beams that are being combined. So we've done a lot of analysis of what happens if the lasers aren't fluctuating in phase, and what happens if they do fluctuate in phase. And of course, you know, I have to acknowledge the very good work that's been done by my former colleagues from the University of Maryland, you know, led by Mikhail Vorontsov, and Thomas is sitting in the audience, Tom Wayrack, who's involved with this work, you know, and they've done a lot of the proof of principle experiments to show that multi-aperture systems can be coherently combined in certain types of situation, okay? And in particular, they've been looking at these master oscillator power amplifier systems where the multiple apertures don't fluctuate independently. If they do fluctuate independently, you have big problems, okay? So this is the model that we've used for a lot of our simulations. We model 9 sub-apertures that are aimed at the target with small tilts, and we use phase screen simulation to figure out what the beam is going to look like in different sorts of circumstances. We also have modeled both lasers that fluctuate a great deal and lasers which, if you like, are phase locked. And we've looked at both Gaussian and Lorentzian line shapes for the fluctuations. I'm not going to dwell on this, okay? And we've looked at what happens if you have these fluctuations, and what happens if you have these fluctuations that it destroys the coherent combining because the things are not fluctuating in phase, and so when they arrive at the target, you still got a big beam, and there's not really going to be any difference between coherent and incoherent combining. So, for example, these are 3 examples of what the power in the bucket would be, okay, for this blue curve is incoherent combining, where you have a certain amount of residual phase fluctuation. The green is coherent combining, where you have some residual phase fluctuation. And the red curve is what if you have perfectly phase-matched beams, which, of course, the red curve would be what you'd get if you had ideal fiber lasers. And if you just look at what happens going through moderate turbulence, okay, and again, these are phase screen simulations. If you look at the beam pattern on target with incoherent combining with a certain amount of phase fluctuation, this is a typical spot that you get. If you do coherent combining with some residual phase fluctuation, you see you're still getting some brightness in the middle of the target, okay? And if you have perfectly phase-matched beams, you have a brighter beam on the target. And this is all done for a C sub n squared to 10 to the minus 14 over a 5-kilometer range. Now, and again, there is a degradation caused by the turbulence. So, for example, these curves show you how much the intensity on the target drops off because of the turbulence, you know, over the perfect beam, and then this is the turbulence degrading your fluence on the target, okay? And in fact, the coherent beam drops off, but the incoherent beam can drop off even more in these levels of turbulence, which I would call medium-level turbulence. Okay? On the other hand, if you go to deep turbulence, and we're talking here about 10 to the minus 13 over 5 kilometers, which is absolutely what you expect near the surface of the sea. People see as much as 10 to the minus 12 near the surface of the sea. So if you're low down, you're dealing with horrible turbulence. And you can see there isn't really any difference between incoherent combining with these phase modulations, coherent combining with these random phases, and this is the perfectly phase match. So this is what you get with your master oscillator power amplifier system. And the million-dollar question is, well, why isn't this better? Okay. I'm going to skip that one. And this is why it's very difficult to coherently combine with very deep turbulence. This system, it's like an adaptive mirror where the individual actuators are spaced by distance d. If this distance d is greater than the Freed radius, you're not compensating for the continuous distortion of the wavefront that you need to go through the turbulence, because all you're producing are discrete changes in piston or tilt spaced by distance d. And it's a little bit like having an adaptive mirror with really too few elements to completely correct for very small Freed radii. Okay? And of course, if you're doing incoherent combining, then in principle, with your adaptive mirror with many actuators, you can control the phase on a much finer scale in order to propagate the beam downrange. And so this is really, I think, a very important conclusion, that you've got to have spacings between the sub-apertures because you've got to deal with the optical damage that would otherwise occur to the optics that are involved in each sub-aperture. And you can only control the phase with this adaptive laser array scheme on this spacing d. And if this Fried parameter gets very small, you're not doing the phase correction with enough resolution to produce the high affluence on the target. And I think, and that's a very important fact, what it really means is that you can do coherent combining if you're working in conditions of weaker turbulence. So, for example, aircraft to aircraft. But if you're talking about low-down paths very close to the surface of the Earth, which might be involved with Navy situations or even Army situations on the ground, you have a big problem if the spacing between the subapertures gets much bigger than the Fried parameter. And so here's a summary, okay? And I've not even talked about what you have to do to obtain coherent combining at the target, because that brings up the question of, even if you can make the combining work, what's the metric that you can use? You don't have a cooperative target, because all you can look at is, diffuse reflections back off the target. And if you've got multiple apertures that you're dealing with, how do you run an SPGD algorithm when you don't have a clear metric coming back off the target? That really creates serious problems. And if you're working with other than master oscillator power amplifier systems, you have a real problem coherent combining. They're not going to work at all. And of course, if you try and aim too far, your adaptive beam correction won't work beyond the Rayleigh range anyway. And so there are a lot of challenges out there, and this has stirred up some controversy, because we published a paper a few months ago pointing out the difficulties of doing coherent combining. And the proponents of coherent combining jumped all over us and wrote a paper saying, no, we were totally wrong. It turned out we didn't disagree with them at all, because they were all working in conditions of weak turbulence. There's no experimental data out there that shows coherent combining working in these really severe deep turbulence situations. And nobody should say it's impossible. There's an old Chinese proverb. Person who says it cannot be done should not interrupt person who is doing it. So we'll stop there. Thank you.